In this lecture, we're going to talk about security from an infrastructure point of view. These are things that are provided, happens behind the scenes, and that you as an application developer really have very little control over. So let's start by just basic cryptography. So uh, there's an easy to remember definition of security, CIA, confidentiality, only authorized users can access data, and resources. Resources will become important uh, later. Uh, Integrity. Data is not corrupted or modified. And availability. You can get at the system and the resources you need when you need it. So that's a brief definition of security. There's a more precise definition, which involves authentication. You are who you say you are. Authorization. You have the right to do what you want to do. Data confidentiality, so that the data is protected. That's the C in the CIA. Data integrity, that's the I in the CIA. Non-repudiation, that means that if you've ordered this book, uh, that you can't deny that you've ordered this book in order to not pay for it. And confident availability, and again, that's the A in CIA. And there's another concept, which is data. So data can either be at rest or data can be in transit. So at rest means it's in disk or in memory. And you don't want to forget data in memory, because it's possible that that could leak out in a variety of ways. Uh, and then data in transit over the network. And so now we come to encryption. And so encryption is a way of encoding data so that it's not readable without a key. And there are three forms of encryption, and we'll go into this. Symmetric, you use the same key, both for encryption and decryption. Asymmetric, you have parallel keys, one for encryption and one for decryption. And then one way, a hash, so that you can encrypt it, but nobody can read it. And there are applications for that. You might say that doesn't make any sense, but there are applications for that. Uh, the U.S. National Institute for Science and Technology, NIST. It used to be the National Institute of Standards a long time ago. Uh, and that certifies algorithms, and not only algorithms, but implementations. So anything associated with security, you do not want to try and roll your own. There are lots of different ways of breaking into code or getting information from about the algorithms. And NIST has experts that will certify that this particular algorithm in this particular context is an appropriate algorithm. So a symmetric algorithm, you have a key, you have some text that you want to encrypt, hello in this case, it turns it into gibberish, then you use the same key and out comes hello. And so you're using the same key for encrypting and decrypting. And this is suitable for data at rest. So if you're storing data, sensitive data anyway, on the disk, you can encrypt it, or you can encrypt a whole bunch of things that are stored on the disk. Doesn't have to be necessarily sensitive data. And symmetric encryption is possible, is a portion of the solution for data in transit. We'll get to TLS somewhat later in this lecture, but that's what you use to protect data in transit. And the NIST approved algorithm is called AES, and they recommend a key length of at least 128 bits. So 128 bits is a big number. The weaknesses of symmetric encryption is that if an attacker discovers the key, then they have access to all the encrypted data. And the second is that authentication can't be done with symmetric encryption. We'll talk about how authentication is done with asymmetric encryption. And then asymmetric encryption is uh, you use a different key. So again, you start with hello, comes out with gibberish, and you use a different key, and it comes out with hello again. That's the encrypted part, and then that's the public. So asymmetric encryption has public and private keys. So the top line is maybe the public key, and the first key is the public key, and the second key is the private key. And the second line of that diagram is the other way around. You start with the private key, you get gibberish, and you use the public key to decrypt it. And so we'll talk about applications of that. And so messages encrypted with the public key can be decrypted by the private key and vice versa. And so there are mathematical relationships between the public key and the private key. And the NIST approved algorithms, there's three of them here, RSA, DSA, and ECDS. And they suggest more than 1024 bits. So you recall that symmetric encryption was 128 bits, but now all of a sudden we need more bits for asymmetric encryption. And then there's hashing. So hashing is a one-way encryption based on a public algorithm, and there's no key. So everybody knows the algorithm, uh, and there's no key involved in it. So there's nothing to keep secret. And it's very difficult to decrypt. Not possible means it's NP hard. So if you know anything about complexity theory, you realize that's hard. Nobody knows exactly how long it would take, but it would take years by some sort of brute force attack to decrypt it. And that's used to verify the integrity of data. So if you have a data item, you encrypt, you hash it, and now somewhat later, you're looking at that data item and you want to make sure it's not changed. So you hash it and you compare it to the hash that you saved originally. Now you have to protect the original hash. I mean, there are some caveats in there, but essentially it's used for the protection of data. So applications, um, instead of saving passwords, you save the hash of a password. And so the site that you're trying to log into will save the hash of the password, and you will enter the password into your browser. It'll get hashed in your browser, and the hash is sent over the network so no one sees the password. And then the recipient checks the hash that is sent over the network with the hash that it created when you created the password. It's used for verified downloads. So you have some software, it's hashed, you have the hash value, you download it, you hash it, and you compare it to the hash that was generated by the author of that software. And presumably the hash that was generated by the author, that software comes in a different channel. And so then you can have some assurance that the software you downloaded is the software that was uploaded and hasn't been corrupted. And the NIST approved algorithm is called SHA-3. And you might suspect that SHA-3 was replaced SHA-2, which in turn replaced I can't say this, SHA-1. And you would be correct. Um, what causes a hashing algorithm to be replaced is that somebody finds a duplicate. The essence of a hashing algorithm is that the things that you hash give you unique values. There are no two unique values that hash to the same value, and that's one reason why you use a lot of keys. Why the hash value is long. If the hash value is short, there are other applications of hashing. But if you look at the performance comparison of encryption algorithms, um, the symmetric encryption is something like 4,000 times faster than asymmetric encryption. And SHA-3 is faster than other hashing algorithms. So when NIST decided to approve a new hashing algorithm because SHA-2 was had somebody had found a duplicate, they looked at performance. The way NIST works is they ask for proposals. Give me a proposal for a hashing algorithm. And then they compare those proposals. And SHA-3 was faster. It was what, better constructed? I don't know. And and that's measured in cycles per byte of value being hashed. So discussion questions, again for offline. Hashing has other purposes than security. So we talked about hashing data to verify its integrity, but hashing is widely used for other purposes. What are they when you're writing code? And then how are the keys in an asymmetric encryption developed? What keeps the keys from being discovered? So look at RSA, for example, for a description of how you would generate an RSA key. So now let's talk about key exchange. So the problem that we're interested in, so the background is that the information that goes on the internet is open to anybody that wants to eavesdrop. You can put a connector. Well, think about Wi-Fi. If you're in a room with a Wi-Fi, you can listen to the Wi-Fi communications of anybody else in that room. Right? There's a protocol that has particular characteristics, and you can do that. You can decode it as well as anybody else. And so, developing a symmetric key is a means of dealing with the fact that eavesdroppers exist on the internet. And so now we have Alice and Bob. Those are our two characters in security scenarios. And they want to communicate securely. But the communication is open to eavesdropping, as I said. And so the first step in their communicating securely is to develop a symmetric key. And this is done by the Diffie-Hellman algorithm. And so they apply Diffie-Hellman, they come up with a symmetric key. And the algorithm, the security of their communication, the algorithm, the Diffie-Hellman algorithm depends on the fact that it's really difficult, again, NP hard, to decode, to do a prime factorization of very large numbers. And so it's based on mathematics of very large numbers. I don't, that's too complicated for me. Maybe it's not too complicated for you. And if it isn't, you can look it up. But I'm going to talk about it in terms of colors. So the colors are going to represent large prime numbers in this case. And the assumption is that decoding a color into its constituents is difficult. So the first step is that Alice and Bob agreed on a shared color. And they then independently get a secret color. So Alice has two colors, a shared color and a secret color. Bob has two colors, a shared color and his secret color. And they mix their color with their secret color. They each mix their secret color with the shared color. So Bob has a color that now represents his shared color, the shared color and his secret color. And Alice has a color that now represents the shared color and her secret color. And then they swap their mixtures. Okay, and this is the essence of the algorithm, that if somebody is eavesdropping, they can't decode what the individual colors were. And now Alice adds her secret color to the mixture that Bob sent, and she has a mixture which consists of the shared color, her secret color, and Bob's secret color. Bob adds his secret color to the mixture that Alice sent, and now he has a mixture that consists of the shared color, his secret color, and Alice's secret color. So they both have the same mixture. That is their shared key, and they use that key. and the eavesdropper can't decode it because it's of the difficulty of taking in this case, a color and break it into its parts. If you're mathematically inclined, you can talk about large prime numbers. And so again, it's based on determining, on the difficulty of determining the constituent parts. If it's prime numbers, then that's the mathematics thing. And if it's colors, then it's more a matter of determining what the constituents of the colors are. So there are other issues. Okay, so how do you generate a large prime number? By large, I mean more than 128 bits, say. And another issue is that the shared key that they generate is ephemeral. So I'll do the ephemeral first, and it's used for a particular session of communication, and then it's discarded. So even if somebody gets the shared key and breaks it, then there's only one session's worth of information. If they communicate again, they generate another key. Uh, and then the second item is how do you generate a large random number? And this gets to the difference between pseudo-random and truly random. So a truly random number is based on physical phenomenon. And one of the discussion questions is what are the physical phenomenon that you can base a truly random number on? A pseudo-random number is based on an algorithm. So you give it a key to start with, and it generates a random number, and then you use that random number to generate another random number. And if you can guess the initial key, the initial seed for the random number generator, then you can replicate it on different computers. If you use a truly random number generator, you can't even replicate it on your own computer. So that's a discussion question. What's the difference between pseudo-random and truly random? And then what are some physical phenomena that are used to generate truly random numbers? And again, these are very large numbers. Okay, so let's move on to PKI. And this gets to one of the characteristics of asymmetric encryption. So Alice has a public key and a private key. Bob has a public key and a private key. If Alice wants, and the public keys are public, right? I mean, that's where the term comes from. If Alice wants to send a message that only Bob can read, then what she will do is encrypt the message with Bob's public key. When the message is sent out over the internet and everybody can read it, then only Bob can decrypt it because he has his private key. So the essence of this is keeping your private key secure. And so that's a way of authenticating, in this case, the reader of the message. You can also authenticate the other way. So if Alice wants to send out a message and guarantee that it comes from Alice, she encrypts it with her private key. And then everybody sees it and can decrypt it with her public key. But using her public key, everybody's public key is different. Using her public key and getting sense out of the message will guarantee that Alice, in fact, sent the message. So you can sign messages and you can direct messages to particular recipients. And that is a characteristic of asymmetric encryption using public and private keys that is not true of symmetric encryption. And so this is a slide that says what I just said. And then we generalize that a little bit into the notion of a digital signature. So a digital signature is a mean for sending an open signed letter. So you have some text, anybody can read it. You want to guarantee that it was sent by a particular individual. So you hash the text and get a hash value, and then you encrypt it with your private key. So a recipient can hash that text, decode the encrypted value with your public key and compare the decrypted hash with the hash of the text that is in the message. That seems a little bit circuitous. Why not just hash the whole thing? And the answer is twofold. Number one, that's for historical purposes. And number two is, well, there are three, I guess. Number two is that it's faster to encrypt a hash than it is to encrypt a long text. And then number three is that it's easier to, if you're a recipient of this message, if you read the message, then you don't have to go through the bother of decrypting it in order to understand it. You can read the message, and in some cases, you don't care who sent it. Okay. And the key to it is that a digitally signed message can't be altered. Because you created a hash of that message, as long as the hash value is consistent between the sender and the reader, then you know the message hasn't been altered. And that's what the encrypting the hash value with public key, with a private key, and then decrypting it with a public key guarantees. And that leads us to PKI. And so PKI is a public key infrastructure. And one element of the public key infrastructure is what's called a certificate authority. So a certificate authority is an independent organization that will issue a certificate only to a party called a subscriber that it can verify its identity. Okay, so certificate authorities are trusted organizations. RSA is one. There are others. There's also a notion of self-sign, of being your own certificate authority, which comes up when we talk about containers and so on. But let's assume that in which case you trust yourself. But let's assume we have an external certificate, an externally generated certificate, and it's issued by a certificate authority. So one use of certificates is to guarantee that a website is what it claims to be. So you own a website, you register the website with a certificate authority, and they issue a certificate that attests to your ownership. So what does that mean? The certificate has the URL of the website that you've registered with them, and it's got a digital signature of the trusted certificate authority. So the certificate authority is attesting through this open letter that you, in fact, own this website. And if anybody wants to challenge that, they can decrypt the hash code of the textual information and verify that, in fact, it was signed by the certificate authority. So you get it. This is a pictorial representation. You get a certificate. Bob registered his certificate with a certificate authority. Bob registers his website with the certificate authority. It issues a certificate. And Alice wants to access Bob's website and wants to make sure that it belongs to Bob. And so part of the handshake, which we'll talk about in a minute, is to send the certificate to Alice, and Alice then checks to see that it's valid. And it hasn't been revoked, so you can revoke certificates, and that's one of the discussion questions. How does that happen? So why do certificates use digital signatures rather than just being encoded? And that's so anybody can read. So there's not a lot of discussion there. And then how's the revocation process? How are certificates revoked? Okay, so this certificates. So we now have the building blocks for TLS, which is the standard method for communication over the internet. And so what are the building blocks? We have the notion of asymmetric encryption. We have the notion of symmetric encryption. We have the notion of getting And symmetric encryption is 4,000 times faster than asymmetric encryption. We have the notion of getting a secure communication, of getting a key, a symmetric key. And we have the notion of certificates and being signed by a certificate authority. Okay, so what problem are we trying to solve? So you're in an airport, you're looking to connect with something, you see something that says free Wi-Fi, and you say, okay, well, I'll do that. And you sign into free Wi-Fi. Well, free Wi-Fi, whoever provides that may be an attacker, and they would receive your communication and potentially get any credentials that you send, and then possibly pass it on to the website you were intended to go to. Uh, but in the meantime, they've lifted your credentials, and then any responses would be sent back through them. And so, as far as you are concerned, you're communicating with your real website, but somebody is listening to all of it and understanding it all. And so, TLS is intended to thwart uh, the man in the middle attack, and it's the basis for HTTPS. So, if you look at your browser, some websites are HTTP, you get to through HTTP, others you get through HTTPS, and HTTPS is based on TLS. So TLS is used in web browsing, it's used in instant messaging, it's used in voice over IP, and those are just some of the communicate of the applications. So it's a standard that's widely used. And it starts with a handshake, and the handshake establishes identity and creates a symmetric key. So first, we have a handshake, and part of that is the certificate exchange that I talked about, and part of that is creating a symmetric key. And then the symmetric key is used to encrypt the actual messages. So symmetric key is faster. Uh, if the symmetric key is secure, then it's better to use the faster method. And so you want most of the communication to be done using the symmetric key. Symmetric key is ephemeral in the sense that it will disappear when your session is over. So if you have a second session, if you log in again or send another email or something like or communicate or connect to the email server again, then you would create a different session key. And so any breakage, any leakage of the session key is limited to a single session. And so the handshake establishes identity. It uses certificates. So this is the asymmetric encryption portion, public-private keys. And the certificates are verified uh, by the recipients, and so it can't be modified or spoofed. And then you use the Diffie-Hellman algorithm, which I talked about, to given that your communication is secure at the establishment of the Diffie-Hellman, then you use the Diffie-Hellman algorithm to create the symmetric key. And again, that's not breakable by a eavesdropper. And so that thwarts the man in the middle attack. So the credential is digitally signed, so they can't alter it. Diffie-Hellman protects against the eavesdropper, in this case, the man in the middle. And your communication with the website is encrypted with a key unknown to the man in the middle, so they can't decrypt your communication. So TLS has gone through multiple versions. And what's the current version of TLS? Again, discussion questions. And suppose the website you're communicating with has not been updated to use the latest version of TLS. What happens? Okay, so now DNSSEC. So DNS is protected. So remember, DNS is the domain name service or name system, I guess. And it's based on root servers, which are physically very highly protected. And they're also highly protected against digital uh, attacks. But they're not protected against somebody who has the right to change a DNS setting, intentionally putting a incorrect DNS setting there. And that's the purpose of DNSSEC. So when you use the DNS system to get an IP based on a URL, you trust that that IP is correct. And DNSSEC says not only do you get the IP address, but you get a certificate of the person that put that DNS entry in. So this doesn't protect against inserting malware, but it does provide a trace mechanism so that if malware is detected, if somebody in fact intentionally manipulates DNS, you know who it was. They have a certificate. They had to verify their identity with a certificate authority, and so you have a means of tracing them. And then the network operators need to enable this. So this is not only a matter of the DNS system, but it's a matter of enabling it through the network because you're sending more than just an IP address. And it's a matter of your browser understanding it. So there's some mechanisms that have to be in place before you can use DNSSEC. But the intention is to provide a trace of if somebody manipulates the IP address. Okay, and now let's talk about a couple different communication mechanisms. So SSH, Secure Shell, that's a standard protocol and it's supporting software that allows one computer to remotely control another, or one individual to remotely control a computer. So you log into your computer, you SSH to a different computer, and you can do anything on that different computer. And it uses a public-private key, but it's different than the public-private key of PKI and TLS. So public-private keys come from from a couple different algorithms, but one of them is RSA. And so when you do an SSH, you create a public-private key. You use that to enable login without actually having a remote login without actually having to log in. And if you've done the assignments, one of the assignments is to generate SSH. If that hasn't been assigned in this term, it'll be assigned when you do when you get to DevOps, unless we've changed something. And when we talk about configuration managers, that's a technique that configuration managers use to control remote computers. So SSH has the notion of a known address. SSH depends on knowing the IP address of the machine with which you want to communicate. And it's used by tools. So could you do all this with TLS instead of SSH? And the answer is yes. TLS allows communication where you don't need to know the IP address of the person you're communicating with. You need to know their URL, but not necessarily their IP address. And so that's part of the handshake process. And so now you're communicating. SSH allows communication between machines. Could I do everything with TLS? And the answer is yeah, but it gets really complicated. So number one, SSH existed before TLS did. So SSH is deeply embedded in practice. You have all these tools that use SSH. It's a standard part of the practice of maintaining a fleet. So you have a fleet is a collection of computers owned by a particular organization that the organization wants to control. And using STLS would mean that you have a lot of certificates. And the certificate, if you get them from a trusted certificate authority, you're paying the trusted certificate authority. And so, that adds to the expense. So if you don't want to do that, you either can self-generate the TLS, self-sign things, or you can use something like SSH. And now there are a couple different ways of transferring files. So FTP, you can see it was standardized in 1971. So as soon as networks came around, somebody wanted to transfer files. People wanted to transfer files. And they said, well, we need to have a standard way of doing it. And FTP came into being. So FTP in 1971, no one thought about security particularly. And so it's it's used for it's built on the notion of a client server. The transfer is not encrypted. There's a notion of a guest inside FTP, so you don't even have to have a password. You just say I'm a guest, and you can transfer files. And that, from a security perspective, wasn't adequate. And so several different secure file transfers protocols came into being. One is FTPS, and that is FTP plus TLS, and that is operating system agnostic. And so it doesn't depend on particular operating systems you have, and you can transfer either text or binary with it. The other one is SFTP, so the S is now at the beginning instead of the end. And it's SSH plus FTP. And that's used for binary transfer between, I want to say Linux, but these days Unix, but these days it's Linux, um, between Linux computers. And if you have a non-Linux system, there are uh, uh, tools that let you do that. So in Windows, it's PuTTY. In the Mac, it's something else. And so, it's not restricted to Linux systems anymore, but it's binary. So discussion questions. What are the use cases for SSH? And talk about or discuss the trade-off between certificates and using certificates and PKI instead of SSH. Uh, Many browsers still support FTP. Does yours? Uh, what is required to use FTP on a browser? And then finally, we'll say just a few words about intrusion detection. So there are two types of intrusion detection systems, IDS. One is host-based and one is network. Host-based is something you're familiar with. It sits on your computer. It scans files. So periodically you will see a message saying in Windows that Windows Defender has not found any problems, or you will get a message from McCaffrey or some other vendor saying we looked and we found 2 or 3 problems, whatever. And it runs on your physical or virtual machine, and it's under the control of the operating system. So it's an application. And it looks for anomalous signatures of files. So first of all, it says, give me a list of all the files on this machine. So discussion question, how does it do that? Secondly, it has a database of known anomalies. So another discussion question, what's an anomaly? And then it looks at all these files to see if they match the database of anomalies. If it does, then it raises a flag. It says this is in a suspicious file. And depending on your settings, it may delete it, it may quarantine it, it may leave it alone, but it'll alert you. And then there's the notion of a network-based intrusion detection system. This is something that the system administrator runs, or the operations group runs, and they look at network traffic. Okay, so network traffic is where they would find somebody trying to break in. So how does somebody break in? They can do a port scan and find an open port and utilize that in particular ways. Maybe somebody's doing a brute force trying to guess your password, so you get a number of failed logins. So if you have too many failed logins, then the intrusion detection system might recognize that. There are other anomalous, there are anomalous traffic patterns. So you're having a burst of a particular type of traffic to a sensitive database, for example, and that is off hours. So you wouldn't expect that. And so that would be an anomaly. The trouble with network-based intrusion, or difficulty with network-based intrusion, is that network traffic is very diffuse. And so it's difficult to detect anomalous patterns. And so you end up getting false positives. Okay, so a couple more discussion questions. Virus scanners look for anomalous signature. What's an anomalous signature of a file? And then when the network IDS detects a potential intrusion, what does it do? It just sits there and says to itself, potential intrusion, or does it do something else? And the question is, what does it do and how effective is that?